Think of nothing. No stars, no planets, no time, no space. Just a complete absence of everything. You might be thinking of darkness or an empty, vast void, but even darkness needs space to exist, and emptiness implies there's still something there. No, this nothing is beyond even that. There's not even the concept of where or when, and yet from this absolute nothingness, somehow everything, the universe, time, matter, energy, was sparked into being. How is this possible? I mean, this shouldn't even make sense. From nothing, logically, there should only be more nothing, right? But here we are, surrounded by galaxies, black holes, and the laws of physics themselves. And that's not all. Not only are we here, but everything seems finely tuned for us, precisely suited for life. The universe appears meticulously calibrated, as if the fundamental constants were set just right to allow stars to shine, planets to form, and life to emerge. But how did this happen? How can something, let alone everything, come from nothing? What forces, if any, could have shaped this cosmic order? And if the universe truly began from nothing, what does nothing even mean? Let's begin from the beginning, or at least what scientists tell us is the beginning. Around 13.8 billion years ago, all of existence, the universe, space, time, and every speck of matter erupted from a single, infinitely dense point. This monumental event, known as the Big Bang, was not just the birth of stars and galaxies, but the creation of space and time itself. Before this moment, there was no before as we understand it, because time as a concept didn't exist. In an instant, this initial singularity expanded at an unimaginable rate, forming the building blocks of the universe. Yeah, I'm sure many of us have heard this same story countless times, and if you're anything like me, you might feel like there's something missing here, like this explanation isn't quite enough. The truth is, there are many creation stories out there. Each culture and civilization across history has had its own take on how everything came to be. In fact, if you were to scroll through Wikipedia's list of creation myths, you'd find hundreds of different versions, some involving gods, others magical forces or cosmic battles. Each one, in its own way, trying to explain the same fundamental question: how did everything begin? We know with certainty that something always exists. Even if we were to remove all particles, antiparticles, photons, and energy quanta from an area, what remains is not truly empty. If we move far from any sources of mass or energy, clear the space of electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, what we're left with is a form of physical nothingness. However, even in this empty space, quantum fields still persist. The constants and laws of physics remain intact. There's a zero-point energy present, a finite and positive value which is never zero. This is likely the closest we can get to nothing within our universe. Even if we try to imagine a more nothing-like state, such a condition doesn't physically exist. No experiment can create or detect it. From a scientific perspective, we can conclude that something always exists, because true nothing has no place in our universe. However, why this is the case is a question science hasn't yet answered. In the universe today, it's clear that space is far from empty. Every direction we observe – stars, gas, dust, galaxies, galaxy clusters, quasars, cosmic rays, and radiation, including the afterglow of the Big Bang. If we had better tools or more advanced technology, we would detect even more signals. These could include gravitational waves generated by masses accelerating through a changing gravitational field, signals from dark matter, and a more detailed understanding of black holes, whether they're actively emitting radiation or not. All of this is happening in a universe that isn't static but constantly evolving. From a physical standpoint, it's fascinating to observe how the universe changes over time. On a large scale, space-time itself is expanding. This expansion means that the proper distance between two distant points increases, the time it takes for light to travel between those points lengthens, and the wavelength of light traveling between them stretches. As the universe expands, it also cools. Light stretches to longer wavelengths, shifting to lower energies and cooler temperatures. The universe was hotter in the past and will continue to cool in the future. As this process continues, matter and energy within the universe come together, forming clusters and creating a vast cosmic web. If you were somehow able to eliminate all matter, radiation, and even quanta of energy, what would remain? In essence, you'd be left with empty space itself, still expanding, still governed by the laws of physics, and still influenced by the quantum fields that permeate the universe. This is the closest physical approximation to nothingness, yet even this state obeys specific physical rules. For a physicist, removing anything beyond this would result in an unrealistic scenario that no longer aligns with our universe. This suggests that what we currently call dark energy would persist in this hypothetical universe of nothing. Even if you set every quantum field in the universe to its lowest energy state, you'd still encounter what is known as zero-point energy. This is the baseline energy that remains, where no further energy can be extracted to perform mechanical work. In a universe with dark energy, a cosmological constant, or the zero-point energy of quantum fields, there's no reason to assume this zero-point energy would be exactly zero. As the universe continues expanding and cooling, there will come a distant future when radiation becomes the dominant force, surpassing other forms of matter, with only dark energy remaining more influential. However, there was another era in the universe. Not in the distant future, but in the distant past, when something else dominated besides matter and radiation. The period of cosmic inflation. Before the hot Big Bang, our universe expanded at an extraordinarily rapid and constant rate. During this phase, the universe wasn't dominated by matter or radiation, but by the energy of the inflation field. This energy was similar to today's dark energy, yet much more powerful, driving expansion at an exponentially faster rate. If the theory of internal inflation is correct, but time is still finite, then the question arises, where did the universe come from? Surely there had to be a beginning, right? To properly address this, it's essential to distinguish three related but distinct concepts: the hot Big Bang as it pertains to our universe, the theory of cosmic inflation and its role in preceding and setting up the Big Bang, the deeper question of the ultimate origin of our universe and why both inflation and the traditional Big Bang might fall short of providing a fully satisfying answer to this question. In the early 20th century, a pivotal synthesis of ideas and observations came together, leading to a transformative understanding of the universe. Four key insights, 1 theoretical and 3 observational, played a crucial role in this breakthrough. Alexander Friedmann's theoretical insight. Using Einstein's general relativity, Friedmann showed that a universe filled uniformly with matter and energy couldn't remain static or stable. It must either expand or contract, with the rate of this expansion or contraction determined by the energy density of space itself. Henrietta Leavitt's period luminosity relation. Leavitt discovered a connection between the period of variation in the brightness of Cepheid variable stars and their intrinsic brightness. This period luminosity relation became a powerful tool for determining distances to far-off stars and galaxies. Vesto Slipher's redshift observations. Slipher measured the shift in the wavelength of light from spiral and elliptical nebulae, later identified as galaxies, relative to our solar system. He observed that many of these galaxies were redshifted, indicating they were moving away from us at incredibly high speeds, sometimes in the thousands of kilometers per second. Edwin Hubble and Milton Humasson's distance measurements. Hubble, working with Humason, used Leavitt's period luminosity relation to study the same types of variable stars in those nebulae, confirming they were galaxies beyond our own. This allowed them to calculate the distances to these galaxies and firmly establish their extragalactic nature. The convergence of these four discoveries led to the formulation of the idea of an expanding universe. As space expands, the matter within it becomes less dense over time. This is because, although the number of particles in the universe remains constant, the space in which they exist continuously grows, leading to a decrease in density over time. This relation was a profound step forward in understanding the dynamic nature of the cosmos. But to fully grasp the concept of the expanding universe, we need to go back to 1927, when a relatively unknown Belgian priest and physicist named Georges Lemaitre proposed a radical new idea. He suggested that the universe had a beginning, a day without yesterday, as he called it. Lemaitre theorized that the universe started from an incredibly small, hot and dense point, which has since expanded into the vast cosmos we observe today. This idea would later be known as the Big Bang Theory. Lemaitre referred to this beginning as the primeval atom, or cosmic egg, where all matter and energy were concentrated in a single point. As he described it, the moment of creation was a profound mystery, something beyond our ability to truly grasp. It was called the origin of everything, and yet no one could explain what came before, if anything. He famously called it the day without yesterday to emphasize that time itself didn't exist before this cosmic moment. After Georges Lemaitre proposed his groundbreaking idea in 1927, the scientific community didn't immediately embrace it. While his theory was intriguing, it lacked direct observational evidence, and the prevailing view at the time leaned more toward a steady-state universe, one that had no beginning or end, always existed as it was. Even renowned physicists like Albert Einstein were initially skeptical. In fact, Einstein famously dismissed Lemaitre's idea, saying, "Your calculations are correct, but your physics is atrocious." However, everything changed in 1929 when American astronomer Edwin Hubble observed that galaxies were moving away from each other. And the further away a galaxy was, the faster it seemed to be receding. This phenomenon, known as the redshift, provided strong evidence that the universe was expanding. And if it was expanding, then at some point in the distant past it must have been much smaller, just as Lemaitre had suggested. Hubble's observations gave Lemaitre's theory the support it needed, and slowly the idea of a universe with a definite beginning began to gain traction. Over time, more and more evidence emerged, and by the mid-20th century, the Big Bang Theory became the leading explanation for the origin of the universe. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided the most definitive proof yet. This faint glow of radiation left over from the Big Bang confirmed that the universe had indeed started in a hot, dense state and has been expanding ever since. This discovery wasn't just a lucky find, it was the cornerstone that supported several major predictions about the early universe, predictions that go far deeper than just the universe is expanding. You see, radiation like photons or light waves does more than just spread out and thin as the universe expands. As space itself stretches, the energy in each light wave stretches too. This is what causes the universe not only to expand and dilute, but to cool as well. It's like watching a rubber band being pulled. Its length stretches, and in the same way, the energy of these light waves stretches as the universe expands, cooling everything down in the process. But now let's do something fun. Imagine we hit the rewind button on time itself. What would happen? The exact opposite of what we see today. If we go backward, the universe won't be cooling and expanding. It will be getting hotter and denser. The further back in time we go, the more compact the universe becomes. All the matter, all the radiation will be squeezed into a smaller and smaller space. The light waves that were stretched by cosmic expansion would get shorter and shorter. As we rewind far enough, the universe becomes so dense and hot that we'd reach a point where all the matter and radiation are contained within a singularity. An infinitely dense, incredibly hot point. This idea isn't just theoretical. This singularity and the conditions it implies gave rise to 5 major predictions about the early universe. And these aren't minor footnotes. These predictions laid the groundwork for what we now understand about how the cosmos began. First, the universe should be expanding. This is confirmed by the redshift of distant galaxies, which we observe as they move away from us. It's like a cosmic Doppler effect, with the wavelengths of light stretching as galaxies get further apart, showing us that the universe is expanding. Second, the universe should have begun in a relatively smooth, uniform state, but over time, this uniformity would break down, and structures like stars, galaxies, clusters of galaxies, and the large-scale cosmic web would form and evolve. This explains why we see a vast, intricate cosmos today, filled with organized structures that weren't there in the early stages of the universe. Third, as the universe was much hotter in the distant past, it would have reached a point where stable, neutral atoms couldn't form. This intense heat and energy led to the prediction of the cosmic microwave background, CMB, a relic radiation that we can observe today. And indeed, Penzias and Wilson's discovery confirmed this prediction. The CMB is essentially the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old and had finally cooled enough for atoms to form. Fourth, in the early, incredibly hot stages of the universe, atomic nuclei couldn't form either. But as things cooled, specific elements could begin to emerge. This led to the prediction of relative abundances of the light elements, hydrogen, helium, and lithium, along with their isotopes. These elements were formed in the first few minutes after the Big Bang, and their predicted proportions line up perfectly with what we observe in the universe today. Finally, the early universe was so hot that neutrinos, the almost ghost-like particles that rarely interact with anything, played a crucial role. They influenced the large-scale structure of the universe and left detectable imprints in the cosmic microwave background. This prediction too has been confirmed in recent studies. So, when Penzias and Wilson found that faint microwave glow in 1965, they were confirming not just one theory, but a whole framework of ideas that explain how the universe began, expanded, and cooled to form the cosmos we see today. With all 5 predictions lining up with what we observe, the Big Bang Theory has become the bedrock of modern cosmology, standing unchallenged since the mid-1960s. But let's take a closer look at what this expansion truly means and how it unfolded. Since scientists tell us the universe began with a bang, it's worth understanding what this expansion really involved. We've all heard about the Big Bang countless times, but here's the thing, it wasn't an explosion as we might picture it. It wasn't like a bomb going off in space. Instead, it was something far more extraordinary. The Big Bang was the rapid expansion of space itself, where everything, from time to matter and energy, emerged from an infinitely small, dense point to create the universe we know today. And this expansion wasn't just a gradual stretching of everything over billions of years. It was violent, rapid, and unimaginably vast. The universe went from the size of a tiny subatomic particle to something about the size of a grapefruit in less than a second. Just think about that. Space itself stretching out, taking time and matter along for the ride. While the evidence supporting the hot Big Bang theory was piling up in the 1960s and 1970s, some perplexing issues emerged that the Big Bang model couldn't quite resolve on its own. There were a few notable observations that didn't entirely fit the narrative of the universe originating from a singular state of extremely high temperature and density. These contradictions gave rise to three significant problems: the horizon problem, the flatness problem, and the monopole problem. First, let's talk about the horizon problem. When we look at the universe, no matter which direction we observe, it appears to have the same temperature and density. The issue here is that regions in opposite directions of the sky should never have had enough time to communicate or exchange information since the Big Bang began. So how is it that these far-flung regions managed to reach the same temperature and conditions everywhere? Second, we have the flatness problem. In an expanding universe, there's a delicate balance between the forces pushing everything apart and gravity pulling everything back together. Somehow, these forces are so perfectly balanced that the universe is spatially flat, neither curved inward nor outward. Why did the universe start with such finely tuned properties? And lastly, there's the monopole problem. If the universe reached extremely high temperatures and energies in its early stages, why don't we see exotic relic particles today, like right-handed neutrinos or magnetic monopoles? According to the theory, these should be around, but they seem to be missing. The solution to these cosmic puzzles arrived in 1980, when physicist Alan Guth proposed the concept of inflation. Guth suggested that the universe underwent an early phase of rapid exponential expansion. During this inflationary phase, space itself stretched at an extraordinary rate, driven by the energy inherent in the fabric of space rather than the usual matter and radiation. Inflation could solve all three of these problems in one go. For the horizon problem, inflation posited that regions that now appear to be disconnected were once causally connected before being stretched apart. This would explain why the universe has the same temperature and density everywhere we look. As for the flatness problem, inflation would have stretched space to such an extent that no matter what the original curvature was, the visible universe today would appear flat. As for the monopole problem, inflation would have cooled the universe before it could reach the temperatures needed to create these exotic relics. This explains why we don't see magnetic monopoles or similar particles today. But this is just the start. Inflation doesn't stop at solving these three puzzles. It also sets the stage for everything that happens next. It laid the groundwork for the cosmos we see now. The quantum fluctuations during inflation seeded the universe with tiny imperfections, which later grew into galaxies, stars, and planets we observe today. Now let's fast forward a bit to the first few seconds after inflation ended. The universe was still incredibly hot, hotter than the core of any star we've ever known. In these early moments, the universe was a chaotic soup of subatomic particles, quarks, leptons, gluons, all interacting in ways that defy our current rules of physics. These particles didn't form stable matter just yet. Instead, they were constantly colliding and transforming into different forms. As the universe expanded and cooled, something crucial happened. Quarks began to stick together to form protons and neutrons. But this didn't happen by chance. It occurred because the universe had cooled just enough to allow these particles to combine. Too hot and they would have kept bouncing around without binding. Too cool and they wouldn't have had enough energy to form stable structures. The timing was perfect. It's almost as if the universe had a built-in balancing act that allowed this process to happen at just the right moment. By the time the universe was 1 second old, protons and neutrons had formed, laying the foundation for atoms. But we still didn't have fully formed atoms yet. For hundreds of thousands of years, the universe remained a dense, hot plasma. Photons, the particles of light, couldn't travel freely because they were constantly bouncing off electrons. It was a cosmic fog, preventing light from moving across space. As the universe continued to expand and cool, it finally reached a critical moment known as recombination. Electrons slowed down enough to combine with protons, forming the first hydrogen and helium atoms. This was when the universe, for the first time, became transparent, allowing light to travel freely across space. This moment is imprinted in the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang, which Penzias and Wilson detected in 1965. This phase, known as inflation, was the catalyst for everything that came after. Without it, the universe would have remained chaotic and disordered, and the formation of galaxies, stars, and planets would have been impossible. In the 1980s, inflation theory made precise and testable predictions about the seeds of cosmic structure observable in the cosmic microwave background and the large-scale structure of the universe. These predictions were confirmed by observations from the 1990s to the present day, further solidifying inflation as a critical element of our understanding of the cosmos. Inflation also redefines how we think of the Big Bang itself. Instead of picturing it as a singular explosion, inflation gives us a new perspective, one where the universe rapidly whooshed into existence, stretching space and time along with it. This phase of rapid expansion not only shaped the universe as we know it, but it also gave us a clearer understanding of how the universe cooled, expanded, and laid the groundwork for everything that would come next. The birth of the first elements. In the first billionth of a second after the Big Bang, the universe was a chaotic hot mess of energy, with no solid matter as we know it today. Imagine a universe so young that time itself barely existed. The laws of physics we take for granted, like gravity and electromagnetism, hadn't even fully formed yet. This period is critical because it's when the Higgs field switched on. This is where we introduced the Higgs boson, the so-called God particle discovered in 2012 at CERN, which took 50 years of hunting to find. Why so important? Because without it, nothing would have mass. The universe at this stage was full of particles zipping around, but they were like ghosts, completely massless. The Higgs field changed that. As particles passed through it, they gained mass, becoming protons, neutrons, and other familiar particles that would eventually form atoms. Now, some scientists argue that the Higgs mechanism is one of the universe's most mind-boggling fine-tuned elements. If the strength of the Higgs field had been just slightly different, we wouldn't exist at all. Too weak, and particles would remain massless, unable to clump together to form stars and planets. Too strong, and the universe would collapse back into itself. It's as if someone dialed in the perfect settings, which raises a lot of philosophical eyebrows. Is this fine-tuning the result of sheer luck, or is there something more intentional behind it? Next, let's zoom in on the first millionth of a second. This is where things start to get weird. The universe was still incredibly hot, trillions of degrees in fact, but now we're starting to see the formation of protons and neutrons, the building blocks of all matter. But hold up, this wasn't as simple as particles just coming together nicely. There's a controversy here that has puzzled physicists for decades. Why did matter win over antimatter? For every particle of matter that formed, there should have been an antiparticle. When matter and antimatter meet, they annihilate each other, leaving nothing but energy. So, logically, the universe should have been left with nothing but a massive burst of energy and zero matter. Yet, here we are, made of matter, sitting on a planet made of matter, observing a universe of galaxies, stars and planets, all made of matter. So, why did matter win? Physicists think that something known as CP violation might be the key to understanding why matter exists. CP stands for change parity, which refers to two symmetries in physics. charge symmetry, dealing with the behavior of particles and their opposites, antiparticles, and paritory symmetry, which is about how physical processes mirror themselves. CP violation means that in certain rare instances, the laws of physics treat matter and antimatter differently, creating a tiny imbalance, about one extra particle of matter for every billion particles of antimatter. But even that slight difference was enough to tip the scales in favor of matter, which is why we're here today. Some scientists speculate that there could be entire regions of the universe composed mostly of antimatter, but so far no evidence has been found to support this idea. Fast forward to the first second after the Big Bang. At this point, things have cooled down enough, relatively speaking, for neutrinos to decouple from matter and fly off on their own path. Neutrinos are some of the strangest particles out there, ghost-like, nearly massless, and almost impossible to detect. Yet they are everywhere, streaming through your body by the trillions every second without leaving a trace. What's fascinating about this period is that neutrinos give us a glimpse into the state of the universe during its very first moment. They're like cosmic messengers carrying information about the early universe's temperature and density. Some theorists even believe that neutrinos could help solve one of the universe's biggest mysteries, dark matter. We'll get back to this later on. And speaking of mysteries, this is also the time when primordial black holes could have formed. Unlike the black holes we think of today, created from the collapse of massive stars, primordial black holes could have formed directly from the intense energy fluctuations in the early universe. These black holes could be tiny or they could be massive. We don't know for sure if they exist, but if they do, they could be the missing dark matter we've been searching for. In fact, some radical thinkers propose that entire galaxies might be held together by these ancient black holes. If proven, it could rewrite our understanding of the cosmos. Now we're moving into the first minute after the Big Bang. This is where the magic happens. The universe has cooled down just enough, to about 1 billion degrees, to allow protons and neutrons to start fusing together from the first atomic nuclei. This process is called Big Bang nucleosynthesis. It's like the universe's first chemistry experiment, but the results were limited. Only the lightest elements could form in this blistering environment, mainly hydrogen, helium, and a smattering of lithium. Here's where things get a little controversial. Some argue that the precise ratios of these elements, about 75% hydrogen and 25% helium by mass, are yet another example of the universe being finely tuned. These ratios had to be just right to allow stars to form later. Stars, of course, are the factories where heavier elements like carbon and oxygen are made, the very elements that life depends on. If the conditions for nucleosynthesis had been even slightly different, the universe might have ended up with too much helium, making star formation and life as we know it impossible. But here's the kicker. Big Bang nucleosynthesis didn't create enough of the heavier elements we need for life, like carbon, nitrogen, and oxygen. That's where stars come into play much later in the universe's timeline. It's as if the universe set up the basic ingredients but left the real cooking to the stars. Without stars, we just have a universe filled with hydrogen and helium. Now that the first atomic nuclei were formed, mostly hydrogen, helium, and a tiny bit of lithium, the next big milestone for the universe would come in the form of the very first molecule. Believe it or not, molecules didn't exist in the universe for the first 100,000 years. The universe was still too hot and energetic for anything to come together and stick. It wasn't until things had cooled down enough that the first molecular bond could finally form. The first molecule to ever exist in the universe was helium hydride, HEH. This simple molecule is a combination of helium and hydrogen, and it played a crucial role in shaping the universe. You might be thinking, what's the big deal? It's just a molecule. But without molecules, complex chemistry wouldn't exist, and neither would life. Molecules allow atoms to combine in various ways, creating the complexity needed to form everything from stars to biological organisms. But why did it take 100,000 years? The universe was still incredibly hot even after 100,000 years. At this stage, the temperature had cooled to about 4,000 degrees Kelvin, still scorching by human standards, but cool enough for atomic nuclei to finally attract and capture electrons, forming neutral atoms. Only then could helium hydride form, and once it did, it served as a kind of chemical stepping stone for the universe, helping to cool things down even further and allowing other molecules to form. Helium hydride wasn't easy to detect, and it wasn't until 2019 that scientists finally confirmed its existence in space. This discovery was a huge breakthrough because it validated a long-standing prediction about the early universe's chemistry. Without helium hydride, the cooling process of the early universe would have taken much longer, and who knows how different things might have turned out. Fast forward to 380,000 years after the Big Bang, this is one of the most significant moments in cosmic history – recombination. We already touched on this earlier, but it's worth revisiting because this moment was truly a game-changer. At this point, the universe had cooled down just enough for the first neutral atoms to form. Before this, the universe was an opaque, dense fog of charged particles, where photons, particles of light, were trapped and couldn't move freely. But when electrons finally combined with protons to create neutral hydrogen atoms, the universe became transparent for the very first time. The formation of these first atoms had a profound effect. The universe became transparent. For the first time in cosmic history, light could travel freely. The photons, which had been bouncing around aimlessly for hundreds of thousands of years, were finally unleashed into the vastness of space. This first light is what we now observe as the cosmic microwave background, CMB, the faint glow of radiation that is still detectable across the universe today, serving as evidence of those first photons breaking free after being trapped for so long. The CMB is often called the afterglow of the Big Bang and is one of the most crucial pieces of evidence we have for the universe's hot, dense origins. When we observe the CMB today, we're essentially looking back in time, seeing the universe as it was 380,000 years after the Big Bang. It's like a cosmic snapshot, capturing the moment when light was finally free to roam the universe. What's fascinating is that this light holds clues about the universe's conditions back then, its temperature, density, and even those tiny fluctuations that would later grow into galaxies and stars. Some scientists argue that the formation of atoms and the release of the CMB was the universe's first moment of clarity. But this raises deeper, more profound questions. Why did the universe become transparent when it did? Was this another example of fine-tuning? If the universe had stayed opaque for just a little longer, would stars and galaxies have formed in the same way? It's one of those cosmic what-ifs that keep astrophysicists up at night. Those tiny fluctuations that we now see in the CMB were the seeds from which galaxies, stars, and eventually planets and life would grow. But without that critical moment of recombination, without the universe becoming transparent when it did, our cosmic history could have taken a vastly different turn. Think about it. If the balance of cooling and expansion had been just a bit off, we might be looking at a universe filled with nothing more than diffuse gas, with no stars, no planets, and no life. The universe's evolution could have been stalled in this early, dense, and chaotic phase. Was this moment of transparency and clarity simply a stroke of luck, or was something more deliberate at play? It's one of those questions that ties right back into the larger mystery of fine-tuning. Everything in the cosmos seems to have aligned perfectly to allow for the universe we see today. And yet, we're still left wondering, was it all a coincidence, or is there something deeper we have yet to uncover? After the release of the cosmic microwave background, the universe entered a quiet yet crucial phase called the Dark Ages. For hundreds of millions of years, the universe was a vast, cold and dark expanse. The light that had just been freed during recombination faded, and no new sources of light existed because stars had yet to form. What filled the cosmos was a sea of neutral hydrogen and helium, slowly being pulled together by gravity. But otherwise, there was nothing to illuminate this early universe. It was a time of silence, with only gravity doing the slow, invisible work of drawing matter together into denser regions. But things didn't stay quiet forever. About 150 million years after the Big Bang, the first stars began to form, marking one of the most transformative moments in cosmic history. Gravity continued to pull hydrogen and helium into dense pockets, eventually igniting nuclear fusion at their cores. These stars were different from those we see today, far more massive, incredibly bright, and short-lived. Their light was the first to shine through the darkness, reionizing the neutral hydrogen that had dominated the cosmos since the CMB. This reionization allowed light to travel freely again, lifting the universe out of its dark period. As more stars were born and died in supernova explosions, they began to enrich the surrounding space with heavier elements, creating the building blocks for more complex forms of matter. These stellar deaths also seeded the cosmos with materials needed to form galaxies. Over the next few 100 million years, these early stars grouped together under the force of gravity, forming the first galaxies. These early galaxies were not the majestic spirals or elliptical galaxies we see today, but rather chaotic collections of stars and gas. However, they were the precursors to the grand galactic structures that would later emerge. With the formation of galaxies, the universe started to take on the familiar shape and structure we see today. Galaxies clustered together, creating groups, and these groups eventually formed vast networks known as the cosmic web. This web, stretching across the universe, continued to evolve as stars were born, lived, and died, enriching the cosmos with their remnants. From the formation of the first stars and galaxies to the intricate cosmic web we observe now, each stage marked another step in shaping the universe we inhabit today. We don't live in a universe where matter floats around in empty space. We live in a universe of energy fields that spread throughout the universe and interact with one another, creating everything we see in the process. Up until now, you might have been picturing the universe as a vast void, sprinkled with stars, planets, and galaxies. But that image leaves out something essential, something that's woven into every corner of existence. The truth is, there is no such thing as nothing. What we think of as empty space is far from empty. Instead, it's buzzing with activity, filled with invisible fields of energy that are constantly interacting, fluctuating, and giving rise to everything we know. These fields shape the very fabric of reality, creating the particles, forces, and structures that make up the universe. Even in the most barren stretches of space where there's seemingly nothing, no stars, no matter, no light, there are still energy fields, like the electromagnetic field or the quantum field. These fields can be thought of as the formation from which all particles emerge, and it's these fields, not solid matter, that are the true players in the cosmic game. Even if we wanted to divide particles down to their most basic components in search of nothing, we would still run into a fundamental truth. No matter how small we go, we can't reach true nothingness. The universe, for all its vastness and complexity, can indeed be reduced to its simplest, most fundamental components. These components form the backbone of reality, and if we can uncover the rules and laws that govern them, we might be able to predict not only the future, but also peer into the distant past. The quest to unlock the secrets of the universe is about meeting this challenge, discovering what everything is made of, understanding how these entities interact, and solving the complex equations that govern their behavior. Conceptually, this makes sense. The universe in many ways follows patterns, And if you can understand these patterns, you can understand everything. The components of the universe aren't as straightforward as they seem. In fact, when we start diving into the nature of reality at its most fundamental level, we quickly hit a wall: the bizarre and counterintuitive world of quantum mechanics. In our universe, the idea of creating or finding nothing is impossible. Everything, no matter how small, is made up of individual entities, quanta that cannot be divided further. These elementary particles include quarks, electrons and their heavier counterparts, muons and taus, neutrinos, photons, gluons, and the heavy bosons like the Higgs. Even if we could somehow remove all of these particles from a region of space, what remains isn't nothing in any meaningful sense. Why? Because space itself isn't empty. First of all, quantum fields are still there. Even when no particles are present, the quantum fields that permeate all of space remain. They are as fundamental to the universe as the laws of physics themselves. You can't remove them because, just like you can't turn off gravity or stop time, quantum fields are part of the fabric of reality. And it's not just quantum fields that remain. Even if you could remove all matter from a region of space, two long-range forces would still linger: electromagnetism and gravitation. We can cancel out electromagnetism in a specific area, but we can't do the same with gravity. Gravity is inescapable, always pulling on everything, even if that everything appears to be nothing. Even if we somehow manage to zero out the electric and magnetic fields, quantum mechanics still throws a curveball. There's an experiment that shows that even the emptiest, most perfect vacuum isn't truly empty. If you take two parallel conducting plates and place them close together in a vacuum, where you've removed all particles, antiparticles and field, those plates still feel a mysterious force drawing them together. This phenomenon is called the Casimir effect, and it demonstrates that even in a space supposedly devoid of everything, something still exists. Let me explain. In 1948, Hendrik Casimir predicted that two metallic plates placed very close together in a vacuum would spontaneously attract one another. No external forces like gravity or magnetism were involved, yet the plates would still be pulled toward each other. This strange effect happens because of quantum fluctuations in the vacuum, vibrations of energy that pop in and out of existence even in empty space. These fluctuations are invisible and imperceptible to us in everyday life, but they become significant on very small scales, like between the plates in Casimir's experiment. In 1966, physicist Steve Lamoureux confirmed the Casimir effect in a groundbreaking experiment nearly half a century after it was proposed. His findings prove that even in the most pristine vacuum, where we've stripped away every possible particle and field, the so-called nothingness still isn't empty. The vacuum itself is alive with unseen, unfelt energy. We may not notice the Casimir effect in our daily lives, but it becomes a major consideration when designing nanoscale machines. For example, tiny sensors that monitor the flow of chemicals must account for these unseen forces, or they risk malfunctioning. The Casimir effect is a reminder that nothing doesn't truly exist, and even the emptiest space is teeming with invisible energy, forever interacting with the universe around it. In other words, the universe simply doesn't allow for nothing. Whether it's the quantum fields, gravitational forces, or the Casimir effect, space is never truly empty. There's always something lurking beneath the surface, reminding us that nothingness is far from simple. It's the most complex something we could ever imagine. Moving on, in 1951, Julian Schwinger, a co-founder of the quantum field theory that describes electrons and electromagnetic force, provided a complete theoretical description of how matter could be created from nothing by applying a strong electric field. Although Fritz Sauter, Werner Heisenberg, and Hans Euler had proposed the idea in the 1930s, Schwinger did the detailed work to specify the conditions under which this effect would emerge. As a result, it's primarily known as the Schwinger effect. Normally, we expect quantum fluctuations in empty space, excitations of any and all quantum fields present. The Heisenberg uncertainty principle dictates that certain quantities cannot be known simultaneously with arbitrary precision. These quantities include energy and time, position and momentum, orientation and angular momentum, voltage and free electric charge, electric field and electric polarization density. While the uncertainty principle is usually expressed in terms of the first two pairs, its other applications can have equally profound consequences. Remember, for any force in existence, we can define it in terms of a field, where the force acting on a particle equals its charge multiplied by a property of the field. When a particle moves through a region where the field isn't zero, it can feel a force, depending on its charge and sometimes its motion. The stronger the field, the greater the force, and consequently, the more field energy exists in that specific area of space. Even in what we perceive as empty space, devoid of particles or external fields, there's still a residual amount of non-zero field energy. Thanks to quantum mechanics and Heisenberg's uncertainty principle, this energy fluctuates in uncertain, unpredictable ways. The shorter the period we observe, the more uncertain the energy becomes, leading to the quantum phenomena of fluctuating fields and the spontaneous emergence of particle-antiparticle pairs. These pairs flash into existence and vanish just as quickly due to the inherent properties of quantum fields. Now imagine a scenario where we take an electric field and continuously increase its strength. What happens next? To understand this, let's consider a simpler example. A meson, which consists of a quark and antiquark held together by the strong force, mediated by gluons. Quarks, as you may know, come in 6 types or flavors: up, down, strange, charm, bottom, and top. While antiquarks are their opposite counterparts with opposite charges. Sometimes the quark and antiquark in a meson have opposite charges, either plus 2/3 and minus 2/3 for up, charm and top, or plus 1/3 and minus 1/3 for down, strange and bottom. If you put an electric field on this meson, the positive end and the negative end will pull in different directions. If the field is strong enough, they can pull far enough apart to make new particle-antiparticle pairs from empty space between them. This means we end up with 2 mesons instead of 1, and the energy needed to make the extra mass with E equals mc² comes from the electric field energy that pulled the meson apart in the first place. Now let's think about an extremely powerful electric field, much stronger than anything we could create on Earth. Imagine considering a full coulomb of charge, around 10 to the power of 19 electrons and protons, into tiny balls, one purely positive and one purely negative, and separating them by a meter. In this region of space, the quantum vacuum would be highly polarized. Strong polarization means a significant separation between positive and negative charges. If the electric field in a region is powerful enough, when you create a vertical particle-antiparticle pair of the lightest charged particles, electrons and positrons, there is a chance they'll be separated so far by the field's force that they can't come back together and annihilate. Instead, they become real particles drawing energy from the electric field to conserve energy. This process generates new particle-antiparticle pairs, and the energy needed for them, via E equals mc², decreases the strength of the external electric field accordingly. That's what the Schwinger effect is all about, and it hasn't been observed in a lab yet. It's mostly thought to happen in the most extreme astrophysical environments, like around black holes and neutron stars. But even then, it's still just a theory, because these places are so far away. On Earth, the strongest electric field we've made are in laser labs, but even with the most powerful lasers, we're nowhere near strong enough. Normally, in conducting materials, only certain electrons can move freely and contribute to conductivity. But if you could create really strong electric fields, you could make all the electrons flow. In January 2022, researchers at the University of Manchester used a smart setup with graphene, a super strong material made of carbon atoms, to achieve this with a relatively small magnetic field that's easier to work with in experiments. And in doing this, they saw the Schwinger effect happen. They made something like electron-positron pairs in this quantum system. Graphene is quite unusual, especially because its sheets behave like a two-dimensional structure. This reduction in dimensions limits the options for the quantum particles inside and the quantum states they can occupy. In a study, researchers used a graphene-based structure called a superlattice, made of multiple layers of materials arranged in periodic patterns. They applied an electric field and observed a unique behavior. Electrons not only flowed from the highest partially occupied energy state, but also from lower, completely filled bands. This led to various exotic behaviors in the material, including a first-ever observation, the Schwinger effect. Instead of creating electrons and positrons, it produced electrons and their considered matter equivalent, holes. Holes are where an electron is missing from a lattice and flows in the opposite direction to the electrons. The observed currents could only be explained by this spontaneous production of electrons and holes, matching Schwinger's predictions from 1951. There are various methods for exploring the universe, and quantum analog systems are among the most potent tools for investigating exotic physics. These systems employ the same mathematical principles that describe inaccessible physical realms, but can be created and studied in a laboratory setting. Testing the Schwinger effect in its pure form is challenging, but graphene's remarkable properties, such as its ability to withstand immense electric fields and currents, allowed it to manifest for the first time in any form within this specific quantum setup. As co-author, Dr. Roshan Krishna Kumar noted, "When we first saw the spectacular characteristics of our superlattice devices, we thought, wow, it could be some sort of new superconductivity." Although the response closely resembles those routinely observed in superconductors, we soon found that the puzzling behavior was not superconductivity, but rather something in the domain of astrophysics and particle physics. It is curious to see such parallels between distant disciplines. With electrons and positrons, or holes, emerging seemingly out of thin air, torn from the quantum vacuum by electric fields, the universe showcases the seemingly impossible, creating something from nothing. When contemplating the vastness of nothingness, the infinite void, the concept of death, it's astonishing how the idea of nothing can evoke such deep fear. When William Shatner, at the age of 90, ventured into space, expecting to witness the mysteries of the universe, he was confronted instead with a different reality. There was no mystery, no majestic awe to behold. All I saw was death. I saw a cold, dark, black emptiness. It was unlike any blackness you can see or feel on Earth. It was deep, enveloping, all-encompassing. Yet, in that particular void, Shatner wasn't actually seeing true nothingness. Instead, he was staring into a vacuum where, paradoxically, so much was happening beneath the surface. Things invisible to the naked eye, yet crucial to our understanding of the universe. This is where quantum field theory, one of the most successful theories in physics, comes into play. It shows us that our universe isn't made of particles floating in empty space. Instead, we exist in a universe of energy fields that span across all space, interacting and creating everything we see, touch, and experience, including ourselves. Some physicists describe these energy fields as fluid-like, akin to water in a swimming pool, while others liken them to a room filled with varying levels of energy, like a field of distributed heat. These fields are never static. They are in constant motion due to quantum fluctuations, brief, almost imperceptible changes in energy that resemble ripples in a wave. These fluctuations occur when external forces, like an electromagnet, excite particles within the field. Even when fields are in their lowest energy state, known as the vacuum state, activity is still ongoing. Pairs of positive and negative particles continually pop into existence, borrowing energy from the vacuum and then vanish, returning that energy back. These fleeting entities are called virtual particles. When the field is excited and hits a higher energy point, it generates ripples that don't cancel out. These ripples give rise to the elementary principles that remain, interacting to create the world we experience. What's fascinating is that the type of particles produced depends on the type of field. For instance, there are different particles for different fields. Electrons, quarks, which form the building blocks of atoms, and neutrinos all stem from specific interactions. These matter particles also interact with force fields, fields of electromagnetism which give rise to photons, the strong nuclear force, which involves gluons, and the weak nuclear force with W and Z bosons. As physicist David Tong from Cambridge points out, without these force fields, particles would simply drift aimlessly through the universe, never interacting or forming anything meaningful. It's the interaction of these fields that makes the universe dynamic and full of complexity. Then there's the Higgs field, which is often compared to molasses spread across the universe. The Higgs field gives mass to particles, slowing them down and preventing them from moving at the speed of light. This process is subtle, but it's essential. Without the Higgs field, the universe would be an entirely different place, with particles zipping around too fast to interact meaningfully. However, not all particles interact with the Higgs field the same way, and this nuance adds another layer to the mystery. Despite all this activity, there's still an element of unpredictability. The particles that make up matter are exceptions, surviving a chaotic dance of creation and destruction. For example, protons form when gluons, particles of the strong force, bind quarks together. Then, through more interactions, protons and neutrons come together to form the nucleus of atoms. It's a delicate balance of forces and particles, and we still don't fully understand why some particles endure while others don't. Even though our universe is filled with virtual particles and fields, the concept of nothingness remains elusive. First, there's the enigma of what came before the Big Bang, a realm that we don't yet comprehend. But beyond that, the nothing we talk about, a vacuum, a space free from matter, isn't truly empty. Quantum energy fields persist, continuously interacting and creating a universe out of what we once thought was nothing. This mysterious nothing may be what gave birth to matter and forces, shaping the universe as we know it. Lawrence Krauss, in his book A Universe from Nothing, suggests that this inherently unstable nature of nothingness is what produces elementary particles. There's even a hypothesis that the entire universe itself may be a grand fluctuation, a cosmic event arising from the nothing that preceded it. This idea, known as the vacuum genesis hypothesis, isn't proven, but it raises profound questions. Could the universe, with all its vastness, complexity, and beauty, really just be a massive fluctuation of nothing? Even if you could imagine a universe with absolute emptiness, devoid of all matter and energy, the laws of physics refuse to allow it. As long as there is energy, be it in the form of quantum vacuum fluctuations or dark energy, there will always be some form of radiation, some trace of something. The universe, in all its phases, has never been truly empty, and as long as dark energy doesn't decay, it never will be. The universe, with all its mystery, is what it is. As we strive to understand it, we must remain humble in the face of the unknown. Our quest for understanding is ongoing, and the more we learn, the more we realize how much there is to uncover. Embrace the curiosity, for it is that drive to explore, question, and discover that pushes us to the edge of knowledge, allowing us to peer deeper into the mysteries that still unfold. This video would not be complete without delving into the philosophical side of the topic. While we have already explored scientific and cosmological perspectives on the origins of the universe, it is essential to consider the philosophical arguments that have shaped our understanding of how something could emerge from nothingness. After all, science and philosophy have long been intertwined in the quest to answer the ultimate questions about existence, reality, and the nature of being. Philosophically, the concept of nothingness has perplexed thinkers for millennia. The ancient Greek philosopher Parmenides, for instance, famously claimed that nothing comes from nothing. According to him, the very idea of nothing was a contradiction. If something exists, it exists. If it doesn't exist, it can't become anything. In this view, existence is eternal and unchangeable, a notion that deeply influenced later philosophical traditions. However, this idea was challenged by others, such as Aristotle, who argued that change is a fundamental aspect of reality. For Aristotle, the universe was not static, and the idea of a prime mover emerged, a first cause, an uncaused cause that set everything in motion. Though this isn't the same as the concept of nothingness, it introduces a key philosophical question. Can there be a first cause, an origin, without something preceding it? And if so, what is the nature of that origin? Fast forward to modern philosophy and we encounter existentialists like Jean-Paul Sartre, who grapple with the nature of nothingness as it relates to human consciousness. Sartre believed that nothingness isn't just an absence, but rather a fundamental feature of being. According to Sartre, we are constantly confronted with nothing in our choices, our freedom, and our future possibilities. In other words, nothingness is the backdrop against which all human action takes place. This view takes the concept of nothingness from a purely cosmological or physical plane to a deeply personal and existential one. The tension between nothing as a physical reality and nothing as a philosophical concept leads to profound questions. Is the nothingness before the universe truly an absolute void? Or is it simply the absence of things as we understand them? Can there be such a thing as absolute nothingness? Or is nothing simply the potential for everything? Even in the realm of quantum physics, where empty space is teeming with virtual particles, nothing turns out to be something. Could it be that, philosophically speaking, nothingness is simply the fertile ground for everything that could possibly exist? Philosophy also forces us to question the limits of human understanding. Are we even capable of comprehending nothingness? Our minds are wired to think in terms of things, objects, events, and processes. The concept of nothing is inherently counterintuitive, and some might argue that the human brain cannot truly conceive of absolute nothingness. Instead, we can only imagine the absence of things we know, space, matter, and time, but not the absence of existence itself. So where does that leave us? The philosophical exploration of nothingness reveals more questions than answers. What was there before the universe? Can something truly come from nothing? Is nothingness merely a human construct, a way for us to make sense of the limits of our understanding? These questions are not merely academic, they are fundamental to how we understand the universe and our place within it. In the end, philosophy doesn't necessarily provide us with definitive answers, but it does offer us a way to think deeply about the mysteries of existence. The idea that everything came from nothing, that the universe emerged out of a void, challenges not only our scientific understanding, but also our deeper metaphysical assumptions. The universe, as vast and incomprehensible as it is, might not have a single explanation that satisfies both science and philosophy. But the beauty lies in the exploration, in the unending search for meaning in a universe that may have sprung from nothing, and in contemplating what that might mean for us as conscious beings. Perhaps the most valuable lesson philosophy offers is this: in the face of cosmic mystery, we must embrace both wonder and humility. For all the progress we've made, the question of why there is something rather than nothing remains one of the most profound and elusive challenges that both science and philosophy will continue to grapple with. We've covered a lot of ground in this video, from the origins of the universe to the mysteries of nothingness. It's been quite the journey, diving into the depths of cosmology, quantum mechanics, and even philosophy. We've looked at how everything we know came from something so unfathomable, perhaps from nothing at all. The universe, with all its complexity, emerged from an explosive beginning, yet that beginning is still shrouded in more questions than answers. It's not just about the Big Bang, particles, or the cosmic microwave background. We've also taken a step back to contemplate the deeper philosophical side of things. What does it mean for something to come from nothing? Is there truly such a thing as nothingness? And how do we even begin to grasp these concepts that defy human logic and intuition? As we near the end of this exploration, it's clear that while we've learned so much, the universe still holds countless mysteries. For every answer, there seems to be a new question that arises. Why does the universe seem so finely tuned for life? Why did it unfold in exactly the way it did? And what does it all mean for us, here and now? These questions aren't just scientific, they're deeply human. They force us to confront our place in the cosmos, our understanding of reality, and the limits of our own knowledge. And while we may never fully grasp the answers, the pursuit of them is what drives us forward. So, as we wrap up this long and thought-provoking journey, remember this. The universe is vast, mysterious, and often beyond our comprehension. But that's exactly what makes it so fascinating. Whether we're looking at the stars or questioning the nature of existence itself, we're all part of this grand cosmic story, one that started from something, or perhaps nothing at all. And the curiosity to keep searching is, in many ways, just as important as the answers themselves. Thank you for watching this video, and don't forget to subscribe for more videos like this.